In today's video, we're going to look at how to construct different polygons inside of circles. So if we get into the first exercise, we have a circle with center point O. Now remember, we would refer to this as circle O because circles are always identified by their center. First thing we're going to do is draw in a diameter. So the most important thing about a diameter is that both ends of the diameter would touch the circle and it would pass through the center. Okay, you can draw any diameter you want as long as there's 2 points on the circle and it passes through the center, then it's technically a diameter. Wherever your endpoints lie, we're going to label them as A and B.
Faith Garcia to the main office, please. Faith Garcia to the main office, please. Thank you.
Now that we have the 2 endpoints labeled, we're going to construct the perpendicular bisector of AB. So a popular construction we've used so far this unit. Remember how it works. We start at either endpoint. I'm going to start at A, and if you chose to start at B, that is 100% okay. I'm going to position my compass with the clear piece here at A, and I want to stretch more than halfway. The nice thing here is we know exactly where halfway is. We have O labeled. You can stretch out further or less. You don't have to match mine exactly, but again, our big thing is that we're more than halfway past O, and I'm going to make an arc. After I make that arc, I'm going to reposition over here at B, and notice I haven't changed the length of my compass. And last step, we're just going to draw a line that connects through those 2 points. Now yours may look different. You might be inside the circle. You may be outside the circle like I am a little bit. You might be on the circle. Any of those 3 variations is all good. But what we do want to be sure of is we want to find the endpoints that they would intersect the circle. So if yours intersected inside, draw your lines far enough so that the straight line continues into the circle. If yours intersected outside like mine did, then you should already pass through the circle. But we're going to label those endpoints on our circle as C and D. And remember, I was referring to this endpoint and this endpoint here where they are on the circle. Now that we have that drawn in, our last thing we want to do is draw the polygon, and we're going to connect A and C. So remember, those are both points that are on our circle. C to B, B to D, and D to A. You might notice that this looks like a familiar polygon. This is a square. All 4 of our sides are congruent, and that's how you would construct an inscribed square. Now let's go a little bit further with this. If I look into exercise 2, we want to understand the logic of why it must be a square. So we want to talk about what triangle congruence theorem could be used to prove that the triangles are all congruent. Now let's look at what triangles we're talking about in the first place. We are talking about AOC as one of them. So I'm just going to highlight. Looking at the other ones, we have BOD, COD, and AOD. We're looking at each of these 4 smaller triangles. So we want to think about things they have in common that would prove all 4 would have to be congruent to one another. One thing is that AO is congruent to OC and OB and OD. Now think about why those might all be congruent and what they have in common. Think about O. It's the center of our circle. The center to an edge of the circle, just like we have in all 4 of these lines, those are known as radii. Okay, the diameter cut in half, which a perpendicular bisector cut that diameter in half. So we should have 4 equal parts. So all 4 of those lines are congruent by having congruent radii. The other thing we should notice is that all of these angles, well, we made perpendicular lines in our construction, so we know not only are these congruent by vertical, but they're all vertical angles that are formed by perpendicular lines. We can say that angles 1, 2, 3, and 4 are congruent right angles because they're formed by perpendicular lines. And if that was the case, if we had all these sides and the angles in between, we know it would be formed by side angle side. So I'm just going to take a second to write that in. So if I go to write that in, all our sides are congruent. So we would say AO is congruent to BO. So all four of those sides congruent by all radii congruent. The other thing we knew is angle 1 is congruent to angle 2, is congruent to angle 3, is congruent to angle 4. Because perpendicular lines form congruent right angles. So that would mean when I answer what triangle congruence theorem, so that's whichever theorem talks about them, that's side angle side. The other part that we should notice is because these triangles are congruent, what can we conclude about those sides? Well, those are all corresponding sides of congruent triangles. We know that those sides are congruent as well. The reason being CPCTC. Corresponding sides of congruent triangles are congruent every time. Now, if I look on to 2B, since we have the triangle AOC, along with the other three we just proved are congruent, are isosceles right triangles. Well, let's take a look at that for a second. So let's look at AOC, we highlighted it here. We know we had two sides we marked that had to be congruent, and we had perpendicular, so it's a right isosceles triangle, so that checks out. If that's true, we want to know what must be their acute angle measures. So let's think about that for a second. So if I had AOC, and I'm not drawing this to scale, think about what we know about triangles. They add to 180 degrees. So we already know 90 can come out because we have that angle. If that's true, and we mark that it's isosceles, what we have to recall is that these two angles here are special because they have to be congruent to one another. They're our base angles. They're across from the congruent sides. So if there's two equal angles, we're going to take 90, the remaining amount, and divide it by 2. So we know each of those angles are 45 degrees. Now, why can I conclude that ACB and CBD and BDA and DAC are all 90 degrees? Well, let's go back to our picture. I'm talking about the angles like ACD. Well, this angle we just showed was 45. This one's also going to be 45. Okay? And same for all of them. So 45 plus 45 gets us 90 degrees. And we know that squares have 90 degrees for all four of their angles. And we showed that all four of these sides were congruent. So a polygon with 4 sides congruent and 4 90-degree angles, that has to be a square. Let's go a little bit further. In our next exercise, we want to talk about triangle congruence a little bit more. So in the diagram to the right, we have a regular hexagon shown. Now remember that word regular. Anytime you see the word regular, it means that all the sides are congruent. So even though we know a square has 4 congruent sides, we could have also referred to it as a regular quadrilateral, 4-sided shape. Now let's look. what triangle congruence theorem could be used to prove that ABC, so this angle here, CDE, and EFA, that they're all congruent? Well, since it's a regular hexagon, all these sides are congruent, and all these angles would be congruent as well. If that's the case, what triangle congruence theorem? Side angle side. Since these triangles are congruent, we know that ACE, the inside triangle, is an equilateral, because by CPCTC, we would have those sides congruent, and a three-sided shape with all congruent sides has to be an equilateral triangle. Again, it can be referred to as a regular triangle, but we know that that term equilateral means the same thing. So I would just write in here CPCTC to get these three sides. Now, I'm looking at exercise 4. We are going to do another construction at this point. So because we're talking about a construction, we're given the circle with center O. We want to draw a diameter in any direction, similar to how we started off the first exercise. So any diameter, just as long as it touches both ends of the circle and passes through the center. We want to draw an arc that's the same radius as the one of the circle. So what I mean by that, if I bring my compass closer here, so from each endpoint of the diameter, draw an arc whose endpoint's the same amount as the radius. So let's start. What I mean by that is start at either end of our circle. Stretch out so that you have the radius in your compass. So we should be exactly at O, the center. And we're going to make an arc until it touches the circle in two places. So there are my two intersections along the circle. I'm going to do the same thing from the opposite endpoint. So we did it from one. We're going to make that same arc, but this time it still passes through O. And it only has that one point of intersection, and that's our other point. We're going to label all these intersections around. So just pick any point you want to start with. So if I started here, I'll call this A. Oops. We've got B. C. D. E, and F. So all 6 of the points are labeled now. And notice I kept them in order. So I did A, B, C, D, E, F. You could have gone in a counterclockwise motion or a clockwise motion. So it doesn't matter the order, but you have to go to point next to. So whatever pattern you start with, follow through. Now we're going to connect all these intersecting points. That way the figure is labeled as A, B, C, D, E, F. So from A to B, from B to C, C to D, D to E, E to F, and F to A. And notice you've just constructed an a regular hexagon. Equilateral would be if it was a three-sided shape, because it's a triangle, but it's regular because all three sides are equidistant from each other. That's why, notice from A, that was the radius, we went 2 points, so 2 radii, AB and AF. Same thing here, we have the 2 sides, and the other 2 are also congruent from each other. So we have our regular hexagon, which is great. Just like you saw in the last example, we want to construct an equilateral triangle. Only thing we do differently from this construction is we would connect the opposite points. So I would connect A, C, and E. You could also do B, D, and F. So that's what you would write in for D. But what I want you to do now is just for number 5, construct an equilateral triangle. Use the same picture we did here, but don't connect all 6. Just connect every other point. Thanks for watching.